Hello everyone, I'm Norman Walberger and welcome to Algebraic Calculus. In this video we're going to look at polynumbers, so extending the idea of polynumbers to two variables or two directions. And then we're going to apply that to the interesting problem of defining and computing tangents to rather general algebraic curves. Okay, so what we're going to do is we're going to start with the idea of a polynumber, which I remind you is sort of a list of numbers written down. And we're going to extend that one-dimensional kind of object to a two-dimensional object, which we'll call a bipolynumber, which is an array that looks something like this. So if this represents the polynumber 1 plus 4 alpha minus 3 alpha squared, then this thing here is going to represent the bipolynumber 4 plus 3 alpha minus 2 beta plus alpha beta squared. So we're going to have alphas corresponding to this vertical direction, just as in the one-dimensional case, and then betas corresponding to this new direction going right. We'll analyze translates of bipolynumbers, that's going to be important, and then we're going to use truncations to algebraically get a hold of tangents to algebraic curves. So we're going to finesse entirely the standard thinking about limits and secants and taking infinite processes. We're going to stick to purely algebraic operations, and the truncation is such a simple and elegant way of doing this. All right, so a bipolynumber is going to be a two-dimensional array of numbers, and it's going to be rather special. We're going to think of it as starting up here and proceeding down and to the right. And we're going to have a kind of a bracket around it to sort of specify how far it extends in these two directions. So I'm going to put a bar on top with a little bracket, and also similarly a kind of a bar vertical with a little bracket. So that's sort of indicating sort of how far this thing extends. Now, we see that the entries here are numbers. That's typically the case. And I remind you that numbers, if we do not say otherwise, includes rational numbers. We prefer to do integer arithmetic, but officially speaking, rational numbers are allowed. Now notice that the spaces here are not occupied. And when we're working with bipolynumbers, just the same way as with polynumbers, additional zeros can be tacked on at the end without changing the fundamental object. So we could put another 0 here, and we're going to consider that to be the same object. This space right here, we could put a 0 there. We could put a space, place that space with a 0. It's still going to be the same bipolynumber. We could also add zeros down here, okay? So we have to be flexible about the nature of zeros. So if you want to know a little bit more about this, Math Foundation 65 talks about these kinds of objects. More generally, or sort of more officially, here's the notation that we're going to use for a bipolynumber p. So just a single letter denoting the bipolynumber. And maybe with aij denoting that the typical element is going to be a sub ij. And notice that the indices are going from 0. So here's A00, A01, A02, A03, A10, A11, A12, A13, A20, A21, A22, A23. So the indices are just the same way as the usual conventions for matrices in linear algebra, with the exception that we're starting with 0 as our first index. Now, we do require that everything be write-downable. We always require that. Okay? So we're not going to, at this stage, be allowing infinite arrays that go on forever. No, they have to be write-downable. You have to get the whole thing on your page. Okay, so that's an assumption that we're going to make throughout. We're never going to talk about things that go on indefinitely that require an infinite amount of time to write down. When we do want to get at so-called infinite things, we're going to have to try to figure out a way of doing it indirectly so that we still end up only writing down a finite amount of information. That's going to be a key challenge for us later on. Okay, but for now, a bipolynumber is just one of these finite specific arrays of numbers which are indexed by 0, 1, 2, 3, and so on. So of course, we would like to do arithmetic with bipolynnumbers. and the simple operations of addition and subtraction are pretty easy to understand. They're just component-wise or entry-wise. And notably, the two bipolynumbers that we're adding, say, do not have to have the same size. The entries don't have to be the same in the same places, because we are agreeing that whenever there's a space, that's really the same as having 0 there. Okay, so let's say we want to add this bipolynumber with this bipolynumber. We're going to get this one, because 3 plus 4 is 7, minus 1 plus 0 is minus 1. The 7 will add to the empty 0 that's in the corresponding spot there to give us 7, and similarly for the 9. The 2 plus the minus 1 will give us a plus 1. The 5 down here plus the empty 0 here will give us a 5. And in this spot there's a 0 and a 6, giving us 6. Multiplication, just as for polynumbers, is more subtle. And it's the same kind of story as for polynumbers. So one way of saying how to do multiplication is the following. If we have a bipolynumber P, which has general component Aij, and another one Q with general entry Bij, then the product P times Q with general entry Cij is going to be defined the following way. So Cij is going to be the sum of all products AKL times BMN, where K plus M equals I and L plus N equals J. So we look for all possible combinations of the indices, so basically that this vector plus this vector equals that vector, if you like to use vector language to think about, that's perhaps useful. And then we take the corresponding products of the entries of these guys, take the sum of all those products to get the corresponding entry of the product bipolynumber. All right, so let's multiply this bipolynumber with this bipolynumber. So I claim that the product is this thing here. So let's see how that would go. So the top entry here, the 0, 0 entry, the only way you can get 0, 0 as a sum of two things is to take the 0, 0 entry and the 0, 0 entry. Multiply those, we're multiplying the 2 times 1, that gives us the 2. To get this 11 entry, that's the 0, 1 entry, we could take the 0, 0 entry and the 0, 1 entry and multiply them. Or we could take the 0, 1 entry and the 0, 0 entry and multiply them. That first product would be 8, that second product would be 3, the sum is 11. So going across a row, that's really just like an ordinary polynumber multiplication. And similarly down here, so this polynumber here is just the product of this polynumber and this polynumber. Well, what about, say, going along here? What about this 11? How would we get that? That's the 1, 1 entry here. We could get the 1, 1 entry by taking the 0, 0 entry times the 1, 1 entry. That would be a product of 0. But we could also get at it by taking the 1, 0 entry and the 0, 1 entry and multiplying those. That would be minus 4. And another way would be to take the 0, 1 entry and the 1, 0 entry. That's a product of 15. So if we add up all those three things, 0 plus minus 4 plus 15, we get 11. You can check that the other entries are the same kind of thing. So there's really some intrinsic geometry down here. So, if we want to calculate a general entry here, what we have to do is we have to think about how that entry can be obtained as really essentially the sum of vectors. How we can write this entry as a sum of one vector plus another vector. And then we would take the corresponding products of fellows over in these two things here. And we would have to take lots of such sums. Now, there's a simpler kind of way to do this, involving a little bit of a mechanical trick that's very reminiscent, in fact entirely analogous, to this sort of reverse strip technique that I showed you for just a one-dimensional polynumber. And that's describable here by showing you this little transparency here. So this thing here is like kind of the reverse of this one here. So instead of 2, 3, minus 1, it goes 2, 3, minus 1. It's like taking this one and sort of rotating it by a half turn. So the way we could get this product using this little strip to our advantage is to place it over this one here and take various products. So the first product that we could do this here. So this 2 is on top of the 1, and the product is 2. If we then are interested in this area, we could go here and we get 2 times the underlying 4 plus 3 times 1. That's 11. Going over to the 12. 2 times 0 plus 3 times 4 plus 0 times 1 would be 12. This one enter here is 11. 2 times 0 plus 3 times 5 plus minus 1 times 4 behind it, a total of 11. This 6, move down here, 2 times 0 minus 1 times 0, 3 times 2, total of 6. Right, so you can just move this thing around in every possible position. You take the products of entries on the transparency times the entry below it, take all such possible products and put it in the corresponding position that you're analyzing. So if you actually had to do bi-polynumber multiplication by hand, and they were reasonably big, this would be a very useful tool. Okay, so now we have bi-polynumber arithmetic. Let's introduce the 2 most important bi-polynumbers, alpha and beta. So alpha is just it's really a polynumber, 0, 1, and beta is kind of a horizontal polynumber, 0, 1, but we're thinking of them as being bi-polynumbers. Then products of alpha are going to be just column vectors, like alpha squared will be 0, 0, 1. Products of beta will be sort of like row ones, 0, 0, 1. And if we take product of, say, alpha with a beta squared, we're going to get this thing here, with zeros everywhere except for a single 1 in the 1, 2 entry. So this has an advantage that we connect with the more familiar story of polynomials that you'll all know. So we could then go back to this multiplication and recast it by replacing these bi-polynumbers with corresponding polynomials in these variables alpha and beta. But the advantage is that we're not really introducing a new concept. A variable is no longer some extra kind of hard to define object. It's actually just a very special polynumber. Alpha is just this polynumber and beta is just this one. So this thing here would be 2 minus alpha plus 3 beta, and this one would be 1 plus 5 alpha plus 2 alpha squared plus 4 beta plus alpha beta squared. And then you can check that the product that we're getting here is just the same as what you'd get if you did ordinary polynomial arithmetic to multiply this polynomial with this polynomial. So this is just a way for us to pin down what polynomials are, introducing this slightly different concept of a polynumber, which ultimately to a computer is just an array of numbers. And so we free ourselves from the dependency on the variables. It's just the numbers which matter. And, well, it's a little bit more cut and dried, a little bit more precise, maybe a little bit more flexible. So now with these simple monomials, alpha and beta, we can create more complicated monomials, just taking powers of alpha multiplied by powers of beta. Alpha to the I, beta to the j. And that's going to correspond to the ijth position in our array. In other words, we can think about all the monomials as forming a geometrical pattern, starting with just alpha to the 0, beta to the 0, or 1 up here. And then alpha, alpha squared, alpha cubed, beta, alpha squared, beta, alpha cubed, beta squared, alpha squared, beta squared, alpha cubed, beta squared, and so on. This is a very nice array because then it allows us to immediately see how a general bi-polynumber corresponds to a familiar polynomial in alpha and beta. You just take the coefficients given by the actual entries of the bi-polynumber and multiply them by the corresponding monomials that correspond. Now, we have this array here. We need to talk about a very important auxiliary concept, that of degree. Okay, that of degree. This thing here is going to be called the degree 0 monomial. And these two are the degree 1 monomials, alpha and beta. Here are the degree 2 ones, alpha squared, alpha beta, and beta squared. The degree 3 ones, and so on. In general, the degree of the monomial alpha to the I, beta to the j is going to be I plus j, just the sum of the powers, or the sum of the exponents. Now, we may also have occasion to talk about these using a slightly different language. So we could also refer to this degree 0 as the constant term. Okay, it's just another term for it. And the degree 1, we could call those the linear terms. The degree 2 would be the quadratic terms. And the degree 3 would be cubic, and so on. Okay, so that's sort of an alternate notation. The degrees corresponding to constant, linear, quadratic, cubic, and so on. So this gives us a kind of a hierarchy of monomials corresponding to the diagonals, or this maybe off cross diagonals, not diagonal this way, in this two-dimensional array. All right, so now let's get on to algebraic curves, which are really the objects of interest for us. So what is an algebraic curve? Well, it's something that's associated with a bipoly number. So here's a bipoly number p. And in terms of alphas and betas, this would be 2 plus 3 alpha minus beta plus 5 alpha squared beta plus 4 alpha beta squared plus alpha beta cubed. All right, so given such a bipoly number, we get an algebraic curve. The curve is just p of xy equals 0, where we agree that when we write p with a comma and two objects, we're going to replace the alphas and betas in this expression with these things, whatever they are, if they're numbers or other variables, whatever they are. Okay? So we're going to replace the alpha with x, we're going to replace the beta with y, and we're going to set that equal to 0. And that equation is for us the algebraic curve. So an algebraic curve is an equation. In this case, the equation 2 plus 3x minus y plus 5x squared y plus 4xy squared plus xy cubed equals 0. That is an algebraic curve. Okay, but what does it look like? Well, to answer that, we have to relate the equation with something geometrical. So we have to say what it means for a point to lie on such a curve. And the answer, of course, is obvious. You all know a point A, say Rs, lies on the curve precisely when P of Rs equals 0. Precisely when the point actually satisfies the equation of the curve. You replace x with r, the number r. You replace y with s, the number s. And the left-hand side actually equals the right-hand side equals 0. If that's the case, then we'll say that the point A lies on the curve. And then generally the idea is, what we're used to, is that we can then plot the points that lie on the curve and we would get a picture. We would get a picture for the algebraic curve. That's the kind of thing that we can do very easily for lines. And we can do it generally for conics too. But unfortunately, the general story is much, much, much more complicated than that. We have to be honest. Okay. So the reality is that most algebraic curves have no or few points lying on them. And getting at those few points, even if they exist, is a major number theoretical headache. Well, not a headache, it's an interesting challenge. But it requires all kinds of powerful theoretical and computational techniques. And it's not generally possible in general. So we may have an equation like this, but actually finding points on the curve can be hugely problematic. But if you ask your computer to graph this thing, it will be able to do so. For example, this algebraic curve looks as follows. So we see something, but what are we seeing? We're actually not seeing points for which this expression is 0. The computer is actually plotting points such that this expression is close to 0. Not 0 exactly, but just close to 0. Making it close to 0 or approximately 0 makes it much easier for the computer to find such points. Then it's a relatively easy piece of cake. It just sort of searches around for points and it can find them. So it's no longer a number theoretical problem, it's just a problem of approximation and searching. But we should not be fooled by this, right? We should not be fooled by the picture into thinking that just because the computer shows us a picture of an algebraic curve and there's lots of points, that there are actually lots of points on that curve in the precise sense that we're talking about here. Okay, that's delusional. Okay, so we have to separate that in our minds. Okay, so that's a very delicate point, and we have to be conscious of the fact that if we're talking about exact pure mathematics, points on algebraic curves are often hard to come by. But nevertheless, sometimes they're there, and we can still ask, how are we going to find tangents to algebraic curves if we do have a point on them? So let's introduce a special definition, a special kind of algebraic curve. We're going to call them grounded. So if we have an algebraic curve, p of xy equals 0, p is some bi-polynumber, we'll say that algebraic curve is grounded precisely when p of 0, 0 equals 0. What that means is that the constant term of p is 0. The degree 0 part, the stuff that's the number actually, which is just in the top left-hand corner, is 0. Or equivalently, that the curve passes through the point 0, 0. Right, this is just the condition that the curve passes through the origin. So if an algebraic curve passes through the origin, we're going to call it grounded. I have to thank Daniel Mansfield for the suggestion of the terminology. It's a good terminology. Okay, so we're going to tackle the problem of defining tangent lines first for grounded curves and then for more general ones. So the tangent line to a grounded algebraic curve at the origin is just the degree 1 part. For example, here is a bi-polynumber, 0, 1, 2, minus 3, 0, 0, 0, 4, 0, 0, 0, minus 1. The corresponding algebraic curve is down here. X minus 3y plus 2x squared plus 4xy squared minus x squared y cubed equals 0. And I can get my computer to graph this, and it gives me something like this. There's a branch up here, and then there's a kind of a nice little curve that kind of wobbles around like that, and then there's another piece down here. Now there very well may be other stuff outside of this. I was just looking at this part of it, and that's what I saw. But in particular, the constant term is 0. Or, if you like, in terms of the expression, there's no actual constant term. The lowest degree are these linear ones. There's no degree 0 term. That means that the curve is actually going through the origin, as we can see here. And what we're interested in is, how do you define the tangent line to this grounded algebraic curve at the origin? And the answer is simple. This definition is telling us just to take the degree 1 part. So here's the degree 1 part, just these two numbers, 1 and minus 3. So if we take the degree 1 part, we get a simpler bi-polynumber. We can call it t of p. There's t of p. We've basically truncated this thing, haven't we? We've taken our line here and we've just erased everything below the line. Erased it all and just left what's here in this top left-hand corner. And there's only going to be 2 entries at most because we already know this one is 0. Okay, so what is this? Well, this is a bi-polynumber. The corresponding equation is x minus 3y, and equals 0 gives us the equation of the tangent line. So that's our definition for the tangent line to a grounded algebraic curve. In terms of the curve, all what we're doing is we're just taking the linear terms and throwing everything else away. It's about as simple as it possibly could be. Okay? You can't think of anything that's simpler than that, I guarantee it. Okay, so x minus 3y, that is the tangent, that's the definition of the tangent to this algebraic curve at the point 0, 0. And let me emphasize, there are no limits anywhere. There's no concept of a derivative. We haven't had to do an infinite number of things. We just look at the equation and we grab the linear terms. Just identify them and take them and throw away everything else. It's a truncation. All right, so how do we use that very special example, that very special situation, to deal with the general case? To define and to determine a tangent line to an algebraic curve at a general point on it. So we have a general algebraic curve and some general point A, R, S lying on it. And we want to know how we're going to define and compute the tangent line to the algebraic curve at this point. So what we're going to do, okay, is we're going to translate the axes so that our point A, which we currently have, is going to be translated or redefined to be the origin A prime equals 0, 0. Right. We're going to shift axes so that we're exactly in the situation that we've just dealt with. We have a curve which is then going to be grounded, and then we can just do this very simple truncation business to find the tangent. So let me illustrate that in this example. So here is a bipolynumber, p 10, 1, 1, minus 2, minus 3. Here's the corresponding equation, or algebraic curve. 10 plus x minus 2y plus x squared minus 3xy equals 0. It's actually quadratic, so this is a conic. And the conic looks something like this. It's a hyperbola, and it happens to pass through the point A, which is 3, 2. Okay. And what we'd like to do is we'd like to find the equation of the tangent line to this curve at the point A equals 3, 2. And our strategy is going to be the following. We're going to translate our axes. Okay? That means we're going to shift our axes so that instead of having an x-axis down here, the x-axis, the new axis, horizontal axis, will be over here. I guess it'll go through 2. Okay. This is going to be a new axis. It's not going to be an x-axis. We might call it x prime axis. And similarly, we're going to translate the y-axis so that it goes through 3. Something like this. All right, that's going to be the new y-axis. We'll call it y prime. And the spacing here, we could just translate that spacing, so it's going to be exactly the same. That would be 1, that would be 1, that would be 2, that would be minus 1, etc. That would be minus 1, etc. So we just translate everything so we have these new axes, x prime and y prime, so that the origin is now exactly the point A equals 3, 2. What it formerly was the point A equals 3, 2, is now in the x prime, y prime coordinates, the point 0, 0. Now, in some cases, another way of thinking about what we're doing would be to leave the coordinate axes where they were and to translate the curve. So instead of translating the axes this way by the vector 3, 2, we could also take the curve and translate it by the vector minus 3, minus 2, essentially move it back, and then it would be down here. The picture that we get is really exactly the same, it's just in different positions. It's often, I think, conceptually simpler for students to think about moving the axes because, well, that's just lines, just moving lines. They're still vertical and horizontal, same parallel as before, while moving curves is more onerous because you have to sort of recompute and redraw. Okay, but they're both equivalent ways of thinking about things. So that's going to be our strategy. So we've translated our axes, and so now we have to ask ourselves, well, now what does the curve look like now in these new coordinates x prime and y prime? We're going to have to do some calculation. Okay, so here is the curve that we started with, 10 plus x minus 2y plus x squared minus 3xy. And here's the relationship between the old coordinates x and y and the new coordinates x prime and y prime. The x coordinate is just x prime plus 3. And the y coordinate, the original y coordinate, is y prime plus 2. And we can check that that's correct by thinking about what happens at the point A. Right? At the point A, the x coordinate was 3 and the y coordinate was 2, while the x prime and the y prime coordinates are both 0, because we've arranged that the axes meet at the point A. And it is indeed the case that 3 equals 0 plus 3 and 2 equals 0 plus 2. So to get the x, y coordinates from the x prime, y prime coordinates, we have to add 3 and 2 respectively. So this is important. This is the change that allows us to replace one set of variables with another. So let's rewrite this equation in terms of x prime and y prime variables. So we just said x is equal to x prime plus 3, so we replace that. We replace the y with y prime plus 2. Here this x becomes x prime plus 3, and we have to square it. And here we have minus 3 x prime plus 3 times y prime plus 2, and still equaling 0. Okay, so now we have to expand this out. We have to know how to expand this using the binomial theorem. We have to do a little bit of expansion here, but it's not very hard. And what we end up getting is x prime minus 11y prime plus x prime squared minus 3x prime y prime equals 0. So let me convince you of say, this x prime. Why is there x prime here? So there's an x prime coming here. But there's also going to be 6x prime when we expand this thing out. We'll get twice the product will give us 6x prime. And over here, how many x primes are there going to be? Well, there's an x prime here, going to multiply what by that 2, and there's also a minus 3, so that'll be minus 6x prime. So altogether, we just get x prime. And how many y primes are there going to be? Well, we have minus 2 of them over there, and there aren't any more over here. And over here, how many y primes are there going to be? There's going to be a y prime times 3 times minus 3, so that's minus 9 y primes in addition to the minus 2, for a total of minus 11. And you can check that these other ones are as I've stated. So this is the new equation of the same curve, but in the x prime, y prime coordinates. And in those coordinates, this is now a grounded algebraic curve because it has no constant term. So we can calculate the tangent immediately. We just truncate. We just throw away all the terms which are higher than degree 1. And we just get x prime minus 11y prime equals 0. So this is the equation of the tangent in the x prime, y prime coordinates. We first have to make the translation, and then we do our simple truncation. But there's still something else we have to do, because we want to translate back into the original xy coordinates. How do we do that? We replace x prime now with x minus 3, and y prime with y minus 2. So the new equation is x minus 3 minus 11 y minus 2 equals 0, or x minus 11y equals 22 minus 22 minus 3, that's 19. And if we bring it to the other side, we'll get minus 19. So we now have solved our original problem. There's the original story. There's the original algebraic curve, that conic. There's the point 3,2. We've now determined the equation of this tangent line. It is x minus 11y equals minus 19. Or in projective coordinates, 1 minus 11 to 19. And that's really the heart of it. That's the heart of calculating tangents to algebraic curves. Now there's more to be said here. So if you do a lot of problems, and in the worked problems and homework exercises in the course, you'll have a lot of opportunity of practicing this technology. You'll start to realize that when we make this kind of computation here, okay, especially if the algebraic curve is of higher degree, that there's actually quite a lot of work involved, and most of that work is going to be ultimately unimportant if we're just interested in the tangent. Because as you can see from here, right, the only thing that we used here to get the tangent are the linear terms. We really couldn't care less about these quadratic terms if we're just interested in the tangent. So that means we could actually have dispensed with a lot of the calculation if we just sort of remind ourselves that we're only interested in the linear terms. And that's, in some sense, sort of the origin of a lot of the formulas for the derivative and so on. They're, in some sense, kind of special little tricks to isolate just the linear terms. But I'd actually rather that you didn't think about it that way, okay? I'd I want you to think about just this in this sort of conceptual way, that what we're doing is we're just making this change of coordinates, and let's just do the entire change of coordinates. And then just extract the linear terms. I remind you that our computers are really, really good at polynomial arithmetic. And making this kind of substitution where you take some algebraic curve and then you make some linear substitution and then rewrite it, that's instantaneous for our computers. They can do this in their sleep in like milliseconds. Okay? So we can exploit that power. We don't have to fumble around to try to get at some tricks. We'll just calculate the whole thing. That has the advantage that later on, as we get a little bit more sophisticated, we're going to be interested in not just linear terms, but also quadratic terms and then maybe cubic terms as well. Okay, so this basic strategy that I'm outlining here now is a very powerful one that we're going to find really helps us understand all kinds of things in terms of understanding local structure of curves. Very powerful stuff. So there's much to learn. I'm Norman Wahlberger. Thanks for listening.